Okay, so let's proceed with our online tuition. So in this particular video, we'll talk about Kpc, the partition coefficient. So let's understand what it is. The partition coefficient is the equilibrium constant between a substance's ability to dissolve in two different solvents. So we have a situation here that looks like this. So let's say you mix an organic solvent like ether and water. You are supposed to get two layers because these two are immiscible. So in this case, our water is more dense, so it will sit at the bottom, and our ether is less dense and it will sit at the top. So just like what you do when you mix your water and your oil. So let's suppose here that we add a substance, chemical A, represented by the purple dots there, that is soluble in both solvents but is more soluble in the ether. So look at these purple dots here. You can see that we have more of them here and less here. So okay, so when you stir the mixture, this is what would happen. Some of the chemical of A will cross over into the aqueous layer, and others will cross, and they will cross backwards into the ether layer. So an equilibrium is set up between these two layers. So these particles are free to jump back and forth here between these two layers. So an equilibrium is set up. So we're going to have a forward reaction and a backward reaction there, where some of the molecules are going into the ether and they are coming from the ether back into the aqueous layer. So an equilibrium is set there. Okay, so as their suspension in each solvent is in equilibrium, we can write the equilibrium constant dedicated to this, which is called Kpc. So Kpc is going to be concentration of A in the ether over concentration of A in the water. So let's look at a specific example. So calculate the partition coefficient when 100 cubic centimeters of solution containing 1,00 gram of chemical A was shaken with 20 cubic centimeters of ether, 0.9 grams of A transferred in the ether layer. So this one is quite simple because we already told how much was transferred into the ether, how much is in the aqueous layer. Okay, so here's what would happen. So the concentration of A in the ether is going to be our 0.9 grams over the 20 cubic centimeters. Technology here, we are not adding the 100 and the 20 because these two are immiscible. So over the 20, we're going to get 0.045 grams per cubic centimeter. The concentration of A in water is 0.1. Okay, so we're going to subtract here our 1 gram minus the 0.1, the remainder, which is 0.1 grams, divided by 100 cubic centimeters of the water, which gives us 0.001 grams per cubic centimeter. So what we can do is now substitute that into our expression for Kpc, and we get a Kpc of 45. There are no units for Kpc because the units will cancel out. Okay, so I'm just going to hint you on a different example, which you can check in a book called written by Roger Norris, where the same situation was created of chemical A, but then chemical A happens to be a chemical that can react, let's say it can react with an acid. Okay, so let's suppose chemical A was a base. So we do the same, we mix, we shake until equilibrium is produced. So in that example, part of this aqueous layer is taken. So we can take, let's say 25 cubic centimeters of this and go and we do a titration. So in the titration, we can figure out how many moles of this chemical A is in the aqueous layer from a titration. So this example can be made complex by giving you a titration part where you figure out how much moles was here, and then now if you know the initial number of moles, you can subtract the number of moles that you figure out from your titration, and then the remainder is what goes into the ether. So this one was quite straightforward. Everything is quite clear, but you may be told that the concentration of, or the number of moles that went into this was figured out through a titration, which you may need to have a balanced equation and your your stoichiometric ratios, and figure out the number of moles from that titration, and then come backwards and still figure out how much remains here. So it can be made complicated, it can be made to be more challenging. So I urge you to go and look at that example, or you can watch my other videos that are coming up where as we explore some past exam questions. So and that is what you're supposed to do. And remember that these two liquids are immiscible, therefore the concentration has to be specifically for the layer that you're dealing with. You don't have to assume that the volume, the total volume is 120. Okay. All right. So let's look at other things that are important for you to understand here. The value of the partition coefficient is governed by the relative polarities of the solute and solvents. So remember, for something to dissolve, there has to be forces of attraction between the solute and the solvent. So let's look at this example. Bromine being added to a beaker of water, the aqueous layer, and carbon tetrachloride there. Okay, so in this example, water is less dense, so it sits on top, as you can see here. Okay. So checking our diagram here, you see that the bromine is more soluble in this carbon tetrachloride layer than it is in the water. So we need to understand that the intermolecular forces between bromine are van der Waals forces, and the same goes for the intermolecular forces that are between your carbon tetrachloride molecules. So which is non-polar. You know, this molecule is non-polar. So the forces here happen to be the same forces, the van der Waals forces between your bromine and the van der Waals forces between your carbon tetrachloride. So what it means is that when we mix the solution, the intermolecular force is broken between the carbon tetrachloride and bromine molecules, are replaced by forces of that are similar in energy. Okay, so this is an error here. When we the forces that we are breaking are the forces between your carbon tetrachloride molecules, and they're going to be replaced by the forces between your carbon tetrachloride and your bromine. So you are replacing intermolecular forces, van der Waals forces, with van der Waals forces, basically. So this is more feasible, unlike what you are doing in water. In water, what's happening is that there's an additional two stronger forces between water molecules. You have your permanent dipole to dipole, and also hydrogen bonding that you have to break in order for you to dissolve your bromine. So the bromine, the intermolecular forces between your water and your bromine are going to replace these intermolecular forces, which are your permanent dipole to dipole and hydrogen bonding. So you're trying to undo stronger forces and replace them with a weaker force. So this is not energetically feasible, or favorable rather. So this is the idea when we say here that the partition coefficient is governed by the relative polarities of the solute and the solvents. Okay, let's add one piece of information here, that in essence the relative solubility of the solute and two solvents will govern the size of the partition coefficients. Okay, so the partition coefficients here are going to be determined by the solubility of the solute in the two solvents. So basically this is it. Okay, so if you understand this, then you are ready to make your calculations for Kpc. Watch out for challenging situations, like we said, where you might need to determine the number of moles in a particular layer through titration. So you can check examples that include that. So I'll meet you in the next video. You can always contact me for further lessons. Enjoy your studies.